Okay, good morning, everyone. So, well done for making it to the end of this course. I've got a different face today. I'm David Silver, and I'm going to tell you a little bit about games, in particular classic games, like the kind of board games which you might play or watch other people playing. And it turns out there's an awful lot of the rest of the course that you can bring to bear in these kind of problems. And so you can think of this lecture as like a case study in how to use all of the techniques that you've learned about so far in trying to achieve or break the state of the art in terms of building algorithms which can actually play classic games to human or superhuman levels. So brief outline. The idea is I'll just start off by telling you a little bit about the state of the art. We're just going to touch on game theory, and really the goal here is to understand, what does it mean to do well in a game? It's not like a single agent domain. It's not like a Markov decision process where there's just one agent interacting with the environment. So what does it really mean to achieve optimal behavior? And that's going to lead us to this principle of minimax, which is the best-known principle of optimality, at least in two-player games. And so to understand the history of games, you really need to understand the history of minimax, because for decades it's been like the way that people have thought about these problems. And so we'll really just touch on how that works and what it means to do minimax search. But then we want to move on to really tying things together with what you've learned about elsewhere in this course. So talking about how do we do reinforcement learning in this setting. And the main idea there is going to be agents that actually learn whilst they're playing against other agents that are also learning. And we call that idea self-play. And it turns out to be a very natural and very powerful way to learn how to find these optimal solutions in these games, these things like minimax. And once we've done that, we'll move on a little bit, and I'm going to try and do some kind of case study in AlphaZero. I'm just checking, actually. I think I might have some old slides here. 1 second, sorry. Let's just check. We'll see how we get on. I think it's going to be OK. So why should we care about games? I mean, I think maybe at least some of you will be sitting there saying, well, I care about the real world. I care about applications. I care about really having impact in the real world. So why all this fuss about games? Why are we using games as the case study? And actually, they make a really useful case study, even if you're not someone who's into games, because they're very, very simple rules which lead to actually very deep concepts. And as a result, they've been studied by humans for hundreds or thousands of years. And in a sense, they're the kind of intelligence domains in which humans really like to test their own intelligence. And there are people who've devoted their entire lives to the study of games like chess or Go or whatever it is. And so it becomes like a meaningful IQ test, a way to compare the intelligence levels of our machines against the intelligence levels of humans. And that makes it a really useful domain. And as a result of all of these things, it's become what's known as the Drosophila of artificial intelligence. The Drosophila was the fruit fly, which was used in genetics research for many, many years. Because it was such a simple organism to study, people really just tried to understand everything there was to understand about the fruit fly before they would move on and study other organisms. And games have kind of the same effect in AI, that people study games because they're the simplest kind of test bed in which you can understand all of the main ideas of AI and machine learning and reinforcement learning, whatever the principles are you want to understand. You can understand them in these games first, and then take what you've learned and push them out into the real world. And that's been shown time and again to actually be the case. And so in some sense, you can think of these as like microcosms of the real world. Like this board game actually is like the real world, but simplified down, distilled down to like its essentials, that there's some simple rules, but they lead to huge complexity, and we can study how to actually achieve intelligence in that domain, this little universe, and it captures at least some of the elements of complexity that we might care about in the real world. And of course, at least to some of us, games are really fun, and so maybe that's the main reason to actually care about them. So I guess I've given this class for a few years, and each time I give it, this slide changes, actually, which is kind of the state of the art in AI. Like, where have we reached in classic games? And so if you think about some of the best-known games like checkers, chess, Othello, backgammon, Scrabble, Go, poker, we've now reached a level of play which is actually perfect in checkers and poker. And what that means, at least for heads-up poker, this is down here when you have two players playing against each other. And what that means is that if you play perfectly, it means that this checkers program, Chinook, if it actually played against God, it would always be able to draw. That's what it means. So that's what perfect play means. Whereas in these other games, like chess, Othello, backgammon, Scrabble, and now Go, the level of play that's been achieved by, and this is the first program to achieve that level, is now superhuman. So we see that across the board, it is possible in these domains to achieve the highest levels of performance. Okay, yeah. So I seem to have my slightly older slides, but anyway, this has now changed as well. So this is what's been achieved using reinforcement learning in games. This is the state of the art so far. So in checkers, we've achieved a level of performance which is superhuman using a reinforcement learning algorithm, an algorithm which has learned by itself to achieve that level by just kind of playing against itself or using self-play. And so that's really, a feat which goes beyond this question of what can be done with handcrafting. Chess, this is the old slide from last time I taught this course, but we just actually in December showed that you could reach superhuman level in chess using principled reinforcement learning methods, and we'll come to that at the end of today's lecture. In Othello, backgammon, Scrabble, Go, poker, all of these are examples where principled reinforcement learning algorithms can now achieve the highest levels of performance. So you don't need to turn or look beyond RL. It's possible to do all of these things with the kind of machinery that you've learned about in this course and nothing more. Really just starting from the beginning, starting from scratch, having a system that learns for itself by actually figuring out its own strategies, playing against itself and actually saying, oh, I figured out what leads to more wins than some other strategy, and playing that strategy more and more and more. This idea is sufficient to reach the very highest levels of intelligence. Okay, so as I said, it's really important to understand what it means to achieve an optimal strategy in a game. So it's not an MDP. So far in this course, you've seen many examples of Markov decision processes, and you've studied what does it mean to achieve optimal behavior. But now we've got multiple players involved. There's multiple different agents all trying to achieve their own goals in this domain. And so when you ask the question, what's the optimal policy in this domain? Well, in a way, it depends. It depends what the other people are doing. You've got imagine this is like a social interaction, and the way in which you can maximize your own gain depends on what the other people are doing in that social interaction. And so there is no absolute answer to the best behavior in that situation. It all depends on what everyone else is doing. But there is one well-known idea which is used and which basically summarizes what people typically mean when they talk about optimality in a game, and that's the idea of a Nash equilibrium, which was famously invented by John Nash a few decades ago. So the idea is to say that if all of the other players fix their policies, that's what this pi minus I means. That means everyone else's policy except for the I player. So if everyone else was to fix their policies, then you could come up with this thing called the best response against that kind of set of policies. So if you kind of just fixed everyone else's behavior, if all you guys kind of fixed your strategies, and I now know that you're all got that fixed strategy, I can compute my best strategy against all of you. And that's a well-defined thing now, because there's no longer this question of what you're doing. That's just fixed. You've become kind of part of my environment. You've become part of the problem that I'm trying to learn about. And so that thing is called the best response. So it's the best strategy for player I against everyone else's strategies. That's called the best response. And so this idea of Nash equilibrium then opens it up and says, well, what if I'm trying to find the best response to you, but each of you is also trying to find your best response against everyone else? And the Nash equilibrium is a joint policy for all players such that everyone has found a best response. So what that means is that we would kind of all try and find the best strategy that we can against everyone else, and we would only be happy, we would only say it's a Nash equilibrium if we all reach a situation where we're happy that we found the best response to what you're all doing. So if I find a situation where I wouldn't choose to deviate from that, I found the best thing I can do against the rest of the population, and each of those other members, each of the other agents in that population has found their best response to what everyone else is doing, that is the Nash equilibrium. So everyone is doing the best thing that they can against everyone else at the same time. And so it's not a Nash equilibrium if there's any incentive for anyone to deviate. So if there's any individual agent that would choose to move away from that strategy because they think they could do better, it's like, oh, actually, I've just noticed that there's some behavior that I can exploit that someone over there is doing. If I find such a way to exploit that and think I can do a little bit better, it's not a Nash equilibrium. It's only a Nash equilibrium if everyone is happy with their strategy, they think they're doing the best thing they can against everyone else's strategy. So that basically is saying, in this notation, that the best response to everyone else's strategy is actually the strategy that's followed by that player. Yeah, question?
So is there always Nash equilibrium for any given game, or are there some games where you can't run
Okay, we're going to, so it's a great question. Is there always a Nash equilibrium? So we're going to consider classes of games where there is always a really well-behaved Nash equilibrium. And so we're going to make lives simpler for ourselves by considering situations where there really is a very well-defined single Nash equilibrium. And it's not always, in some games there can actually be many, many different Nash equilibria, which is quite interesting. For example, the game of poker, there's many different Nash equilibria, and sometimes some of them are seem like they're better than others. Like you can have one where there's the famous problem called the prisoner's dilemma and things like this. There's situations where all the players can be happy with how they're doing and they wouldn't choose to deviate, but still there's kind of this fallacy of the masses where they're all doing very badly. And that would still be a Nash equilibrium because no one would choose to deviate from that situation. And there might be another situation where if everyone would also be really happy with where they've got to, and that might be a different Nash equilibrium where everyone gets an objectively much better reward. But they're both Nash equilibria. So you can get these quite complicated games like poker that have these properties, and that typically arises when you've got imperfect information, where you've got partial observed stuff going on where I don't know all of the information that you have and vice versa. When we have perfect information, we're going to consider classes of games where there's always a single Nash equilibrium and we've got principled ways to find it. So that was a great question. Okay, so if we think about how does this fit into our usual framework of reinforcement learning, we can think of that this best response thing is basically what happens when we try and solve a single agent RL problem where the other players have just become part of the environment. So imagine there's a two-player game or something, and now there's black and there's white, and white is saying, okay, well, I'm just going to treat black as some fixed strategy and find the best response to that strategy by black. And so black kind of becomes part of white's environment. Black becomes kind of part of the background in which white is operating and trying to get reward. And if black is always playing in the same way, well, it's just like some MDP that white happens to be in which black is always taking these same things, and that leads to some situations that white now has to deal with. So the other players become part of the environment when you're trying to find the best response. So you can always think of this multi-agent thing as reducing to a single agent problem whenever the other players are fixed. So if you fix the other player's strategy, it's just an MDP. And the best response is actually the optimal policy for this MDP. But in practice, we don't want to fix the strategies of the other players. We want to know what happens, what's the best strategy for me when everyone else is behaving really well. It's not interesting to ask what's the best strategy for me when everyone else is behaving in some kind of dumb way. What's the best strategy for me when everyone else is behaving really well? That's, again, the Nash equilibrium. So you can think of the Nash equilibriums like the kind of fixed point of self-play reinforcement learning. So how can we think of that? Well, the idea is that you have your agents in your game, and experience is generated by playing games between agents. Okay, so whatever the strategies are for our agents, so we've got these strategies pi 1, pi 2, and so forth, and we're going to use those current strategies to generate experience. So you generate that experience, and from that experience, each agent is going to treat what it's seen, is going to try and learn about those other strategies as if it was in an MDP where those other strategies were fixed. So if you're pi 1, you're just going to kind of assume that pi 2 and pi 3 and pi 4 were fixed and try and find the best response to those. But in the meanwhile, the player who's generating pi 2 is also going to treat pi 1s as if that was fixed and try and learn how to do better and try how to beat pi 1. So kind of pi 1 is treating pi 2 as fixed and trying to beat that current strategy of pi 2s. In the meanwhile, pi 2 is treating pi 1 as fixed and trying to beat that strategy, and so forth. So everyone is just generating experience according to their current strategies so far and trying to beat the strategies of the other players. And so this process kind of goes on and on and on. And so you can think of this as one player's policy determining the other player's environments. And so all these players are adapting to each other, and if at any point all of the players have no incentive to adapt anymore, if they're all happy, then we've reached an equilibrium. So in particular, we've reached the Nash equilibrium. And so the Nash equilibrium is the fixed point of this process. And so this is kind of independent of what the learning algorithm is. It might be that any particular learning algorithm might fail to find this fixed point. So it's a hard learning problem to actually find this fixed point. But still, it is the fixed point of this self-play reinforcement learning. If each player is trying to optimize against the others, and at the point where they're all happy and declare victory, it's like, if if player pi1 says, OK, I'm done. I've achieved everything I've learned about against pi2, and pi2 at the same time says, I'm done. I've learned everything I can do against pi1, that means they've reached a Nash equilibrium. By definition, they've got no incentive left to change, and they wouldn't choose to deviate anymore. And so they have reached this jointly kind of optimal policy, the Nash. Yeah, question?
So the Nash equilibrium is met because of the idea that in a reinforcement learning setting, we're always optimizing. Is that the idea?
Yeah, exactly. The idea is that in reinforcement learning, we're trying to optimize for some MDP. We're trying to find the optimal policy for some MDP. And so the idea is that in that MDP, we are like, each agent is finding the best response. So optimizing that MDP is equivalent to finding the best response. And the Nash equilibrium is kind of where everyone has found the best response to everyone else. So that's the idea, that the RL is the way that we kind of reduce each player's perspective to an optimization of an MDP to give us this best response. And by jointly doing that, we find the Nash. Yeah, question?
Yeah, obviously, if the opponent does a Nash equilibrium, then I can see how it finds the fixed point. But if in RL, if the opponent is suboptimal, will it be optimal? Will it do better than the Nash equilibrium and find the Nash equilibrium as a kind of base case only in the case where the opponent is optimal? How can it do better?
So the question is, can it learn to, so it's a fixed point, but does that necessarily mean that you actually start to improve towards the fixed point, given the learning algorithm?
No, it's more if your opponent isn't doing Nash equilibrium, it's your worst case that you do Nash equilibrium, but we're using RL, you're more general, and you can do better against an opponent who doesn't do a Nash go for optimal.
Oh, I see. So RL is a more general framework. For example, if it was the case that you just chose some strategy for pi2 and you wanted to know how could pi1 exploit some suboptimal pi2, you can ask your RL algorithm to find the best response to pi2, and it will go ahead and do that, and that will be better from pi1's perspective than playing Nash. So it can do that. But if you allow both players to evolve against each other, the idea is that it will eventually find a Nash equilibrium. And so you can choose to do other things than find Nash. The purpose of this slide is to show that there is one natural choice, which is to try and find the Nash equilibrium. And so this is like a mainstay. Like if you go and study maths or something, or even watch movies about John Nash, who seems to appear regularly in Hollywood, then the Nash equilibrium is the big conceptual idea that helps people understand game theory and societies and how people interact with each other and so forth. In economics, this is a very important concept. OK. So as I mentioned, we're not going to consider this very general case of all games. We're going to focus on a special class of games. So the special class we're going to consider, we're going to start by thinking about perfect information games. So these are games that are fully observed by all players. So for example, something like chess or Go have perfect information. What that means is that all players can observe all of the information that's available to all the other players. There's nothing private that's available just to one player. Whereas if you think about a game like poker, I have my private cards that the other players don't see, and that private information is what's called imperfect information. There's some kind of hidden state that's not visible to the other players, and that gives rise to these very complicated dynamics where I now have to reason about, what cards might you have, and in that situation, what should I do? And if there's time, I might touch on this at the end, how to deal with imperfect information games. And I just want to kind of give you, the teaser here, which is all the same methods that we talk about extend very naturally to the imperfect information case. So it's not like they just fall over. Just as we saw in RL, in reinforcement learning, by building a state representation that takes account of the history of observations, you can deal with partial observability. And the same kind of thing helps us to deal with imperfect information games. We just need to kind of do things in the right way. We're also going to focus on two-player games mostly, where we have two alternating players, so we can think of them as white and black without loss of generality, and they take turns to play. And we're going to focus on what are called zero-sum games. So in a two-player game, a zero-sum game is basically a game that has equal and opposite rewards for black and white. So it's called zero-sum because the reward for player one at any step plus the reward for player two has to equal 0. In other words, what's good for black is bad for white. So if I win, you lose. That's basically what a zero-sum game is, and vice versa. You can have more general zero-sum games where you can have many players, and as long as the rewards for all of those players sum to 0, it's still zero-sum. In other words, if one player wins, all the other players lose is the most common way that they only it has to sum to, the utilities have to sum to 0. And so the question we ask now is, in these special cases, how could we find Nash equilibrium in perfect information two-player zero-sum games? And the two ways which we're going to talk about are game tree search, like a kind of planning, and this is like historically the method which has been most widely used for decades, and self-play reinforcement learning, which is the kind of the version which you've been learning about in this course, but extended to this self-play context. And combinations of the two are also possible. Okay. So let's see if we can bring back the machinery from the rest of RL and bring it to bear in this setting. Like, what can we do to actually think about things like value functions and policies when we move to this multiplayer setting? And so the first thing to say is we can come up with the same concept of a value function. This is going to be really crucial to us. And the value function, as always, is going to be the expected total reward that we get. Like if you play a game now, how much reward is a particular player going to get? And note that we don't need to think about separate rewards for the two different players, because R1 is just equal to minus R2. So we can just always think of the reward from one player's perspective, and that's going to be fine now. We don't need to, the other player's perspective is always going to be the negative of that. You can generalize this to the other case, but just to keep things simple, there's one value function, and the value function for black is just minus the value function for white. Okay? And so we want to say, well, how can we maximize the total amount of reward we get? And we're just going to think about having a policy pair now. So our policy is going to be player 1 follows pi 1, and player 2 follows pi 2, and that kind of determines completely how they're going to play this game. And there's also some game rules that you can think of as like the environment that determine, how the state's going to evolve, given actions played by player 1, actions played by player 2, and the rules of the game. That entirely determines how the game will proceed. And then you can ask the question, well, under that policy pair, who's going to win, basically? What's the expected total reward going to be? Which is typically just, rewards in these games are very often 0 all the way through, and then at the end of the game, +1 for winning or a -1 for losing is the canonical case we'll think about. So we can say, well, there's this value function, which is just the expected reward, the expected return. So this is +1 for winning, -1 for losing. And it's the expected return under, if there's any stochasticity like dice in the rules, like if you're playing backgammon and you want to know what happens under the dice, the expectation would be over those dice. And if there's any randomness in your policy, the expectation would be over the randomness in both players' policies. And we can ask, well, if we average over all of those sources of randomness, who's going to win? And that tells you, well, how good is this policy pair? Like, who does this favor? Like, if the answer is that you get more +1s than -1s, in other words, if it's really favoring white over black, then that tells you something about this value function, that this policy pair is a good policy pair for white and a bad policy pair for black. Okay, so the special thing about these two-player games is that there's actually something which we call the Minimax value function. And what that does is it maximizes white's expected return while minimizing black's expected return. Basically, the way to think of this is that the Minimax value function, there is a unique value function, and the special thing about the Minimax value function is it uniquely determines think of it this way, that if black played the best possible strategy for black and white played the best possible strategy for white, what would the final outcome of the game be? And that's what the Minimax value function tells us. And the amazing thing about it, the amazing thing about the Minimax value function is that it's unique. And this is not true, for example, if you're playing a game like poker with imperfect information or non-zero-sum games and so forth. This gets more complicated. But for this class of games, there is a unique value function. There's a well-defined question, which is just how good, who's going to win from this position under best play by both sides. And then the Minimax policy is really just any policy pair, like a way to play for black and a way to play for white, that achieves those Minimax values. And there might be more than one, so this might not be unique. Just like in an MDP, there's one unique value function. There might be many policies that achieve it. And the same is true in games. There's one unique Minimax value function, but there might be many ways to achieve it. The simplest example being, like imagine you're playing tic-tac-toe, and the first player, plays in the middle and then goes on to, the other player will block somehow and ends up being a draw. And there are many ways that you can reach a draw. There's not just one strategy that reaches a draw. There are many. But the minimax value function is a draw for that game. And there was a question, I think. Sorry, yeah.
Yeah, so the minimax value function, does it assume that white knows what black's policy is?
No. So the minimax value function it's sort of defining a policy for black and white in some sense. It's saying under best play for black and white, this is what could be achieved. So it's not kind of given a particular strategy for the other player. It's saying under all possible strategies for both players, what's the best outcome.
And then like the best thing for white, is that given black's policy and vice versa? Like is it a kind of Nash equilibrium too?
It is a Nash equilibrium, yes. So the minimax policy is a Nash equilibrium. Yeah, it's exactly a Nash equilibrium. And that's actually what I wanted to change this to, is to say the correct definition here is that the value function for black is basically the thing which maximizes the value over all policies that black can do against white's minimax value function, and vice versa. Anyway, I'll correct that in the slides when I post them. So just to make that clearer, we can think about actually doing minimax search. And again, this is like if you pick up any AI book from the last 50 years until people started like rediscovering machine learning and deep learning and all these new ideas, this was like chapter 1. Like this was the thing that you would learn about and would be like definitional about what AI is, would be, oh, you really need to learn minimax search because that helps you understand how chess programs work and so forth. And minimax search is really, it's a mechanistic view of the minimax value function. And it's basically saying, well, one way to view the minimax value function is to say that you can think of it as like, we can draw out the entire game tree as saying, well, from this situation here in tic-tac-toe, there are all of these different situations where crosses can play. And from each of these situations, there's a bunch of places where the O's can play. And it's not showing everything here where the noughts can play. And if you to actually write out that entire tree, then you can look at the bottom and you can see what the values are at the bottom. And you can kind of propagate all of those values back up to the top to compute that if one player is maximizing and the other player is minimizing and the other player is maximizing, there is some optimal way, some optimal strategy for computing the value function. We'll run through an example in just a second. But actually, this was first introduced by Claude Shannon. I mean, actually, if you look at the history of computer science, like all the great computer scientists like Turing, Shannon, Babbage, von Neumann, they were really, really interested in games and game theory, and they were fascinated by how to make machines play chess in particular, but all kinds of games. And so Claude Shannon actually, he came up with this minimax search, and this was actually ran on paper, this algorithm at that time, but it went on to become the mainstay of sort of every single chess-playing program in the world for like 50 years, pretty much until December. So this is an example of Minimax. So this is like a very simple game tree now, just some abstract game with just 2 choices for each player. And you can see there's 2 choices for the max player. And from each of those states that you reach, there's 2 choices for the min player. And from each of those states, there's 2 choices for the max player there. And at the end of it, there's some outcome, there's some reward that you get at the end where this is the reward from one player's perspective, from the max player's perspective of +7, +3, and so forth. And so from this, you can kind of compute by a kind of depth-first search what all the values are. So we're not actually going to do the whole depth-first search, but we can kind of run through this idea to say, well, you know, from these leaf values, we can compute, you know, that the max of +7 and +3 is +7. So max would always choose this action here, and never choose this action here because this is the thing which gives more value from his perspective. And so Max would choose -2 out of -2 and 4, and +9 out of +9 and +5, and so forth. And then we can propagate those from min player's perspective as well to say that from min player's perspective we choose -2 rather than +7, because from the min player's perspective, you know, +7 is a terrible result and -2 is a really good result, and -4 is a better result than +9 from the min player's perspective. And then you can propagate this again to the root, and this gives us a max of -2. And so this really is the optimal value. So hopefully this helps to understand what the minimax value actually means. That it means that max is choosing its value, assuming that min is minimizing, and while min is assuming that max is maximizing. And now if you propagate that all the way back up to the top, you get this unique optimal minimax value. Yeah, question?
2 slides back, could you quickly say again how you changed the formula, like how you would want to amend it?
I'll send it on a slide. It's easier, I think. It's the easiest way to understand it is like this, that it's, at least in a deterministic game, that you're maximizing over the minimum of the max of the min of this action series. So kind of the first player gets to choose the first step, the next player gets to choose the next step, the next player gets to choose the next step, and so forth. And so you've kind of got the max of a min of a max of a min of that sequence of actions. In the stochastic case, you just kind of need to amend that a little bit. So this gives us like a mechanistic principle then for how to compute this minimax value. But it's clear that the search tree grows exponentially. And in any game of reasonable size, it's impractical to search to the end of the game. So what do? It might be about tractable in tic-tac-toe, or noughts and crosses here, but it's not tractable if you go to any game of meaningful size. And so in practice, what people use is something which we would call a value function approximator, but which in all of those AI textbooks, if you ever pick them out, would be called an evaluation function or a heuristic function. And so the value function approximator is trying to approximate this minimax value. So we could say from each of these states, instead of actually computing this thing exactly, we can have some function approximator which estimates each of these values in each of these nodes here, based just on, say, the board position. So if you're playing chess, you could kind of look at the position in this situation, and from that situation, without even looking at these other possibilities down here, try and estimate what the value is. So that's a value function approximator. So it's a function that takes these parameters w and feeds into this position s, and that would be the value function approximator which people would use instead of in place as like a proxy for doing subtrees of this minimax search. And so what you can do is if you had a very large search tree, imagine that you were able to search down to this depth, but you couldn't search all the way down to the end of the game. What would you do? Well, you would search down to here, and instead of going to the end of the game to figure out the true value here, you would replace your value here with your value function. Your value function would give you some value here, and then you'd propagate that value back up using your minimax search procedure instead of the real value. So what this tells us is that we use the value function to estimate the minimax value at leaf nodes, and then the minimax search typically would just run to say to some fixed depth with respect to those leaf values. Is that clear? This is a very, very common idea. So let's make this concrete and also help to give some historical context by thinking about the simplest and also most common way in which these evaluation functions were built up in the past. And that is using what I call a binary linear value function. So you have some binary feature vector, which, for example, would look something like this. So some binary feature vector telling you which features are present in this position. So in particular, we could think of this feature here as saying, does white have a rook in this position? And this is a 1 because in this particular position, white does have a rook. And then there's a white bishop kind of indicator. And again, white has a bishop in this situation. But white doesn't have a pawn, so there's a 0. Black does have a rook, so there's a 1. Black does have a bishop. Sorry, black doesn't have a bishop or a pawn. And so that kind of summarizes, these are just features summarizing what's going on in this position. And you could imagine there could be much more complicated features, but here these are the best known features from, like if you learn how to play chess, you basically learn to assign material values to each of these. And so the first thing you do is say, well, what's present in the position? And then, as a human, when you're learning how to play chess, you're told the values of each of those things. So you're taught that, a white rook is worth +5, a white bishop is worth +3, a white pawn is worth +1, and then we flip the perspective when we think about the opponent, and we subtract off 5 if the opponent has a rook, subtract off 3 if the opponent has a bishop, and subtract off 1 if the opponent has a pawn, etc. And so to evaluate this position as a human, the way you're kind of taught when you learn how to play the game of chess is we take the inner product of these two things. So each of these features times its value, and you sum it together. And so what this is really telling us is that for each feature that's actually present in this position, we accumulate its weight. So we're summing together the +5 for having the rook and the +3 for the bishop, take away the -5 for this rook, and that tells us that white in this position is kind of winning by +3, if you like. So this is the classic binary linear value function. And at the end of it, you'd probably squash it down into something that actually estimates who's going to win in that position, like some kind of sigmoidal activation function to squash this into a +1 for winning and -1 for losing. But that is kind of the classic way by which all games were evaluated. And the only thing which changed from this is that the set of features became much, much richer, and grandmasters went to great length in all of these games to try and handcraft very, very specific values for these weights. And they would play around with it, say, no, I think actually the rook isn't worth +5, it's actually worth +4.8. And then they would slowly tune their program to get better and better. Yeah? So in this, the king would have infinite weight because in chess, if you don't have a king, you've lost the game. So I guess you could think of that as infinite, but in practice, it would never even occur because you, inside your search tree, you would never see positions without a king. So it kind of just factors out. So the most famous game-playing program of the last era was Deep Blue. And this was the first program to defeat the world champion at the game of chess. And I think it's useful just to understand what went into it, because it was exactly what we've talked about so far. That really, it had about 8,000 of these handcrafted chess features. So instead of just having the piece values, this vector was about 8,000 long with all kinds of handcrafted features, talking about things like king safety and pawn structure and all this kind of other stuff going on. And it had a binary linear value function, and the weights were largely hand-tuned by human experts, although there was a little bit of machine learning they experimented with. And then there was this really high-performance alpha-beta search. What's alpha-beta? Alpha-beta is something, again, which would be in your chapter 1 of these textbooks, but it's basically a way to efficiently compute this Minimax search tree by automatically pruning parts of the tree that you don't need to compute. That you can already know that certain parts are never going to be taken by the max player because you know that min would never even let you go down that part of the tree, in which point certain parts of the tree can be excluded altogether from computation. And it's a dramatic improvement over the naive approach. So Deep Blue did this. It was this high-performance parallel alpha-beta search, and it was specially made hardware, searched around 200 million positions a second. It looked ahead about between 16 and 40 steps into the future in this search tree. And at the end of each of those positions, it used this binary linear value function to kind of estimate who was going to win, propagate that all up, and use that search tree to decide what to do. And at the end of that, it defeated the human champion in 1997 by about 4 games to 2. And at the time, it was actually the most watched event in internet history. So this was considered a real watershed moment by many people. Okay. I think it's also worth mentioning that Deep Blue was not the only example of this strategy, that this was applied separately in many, many different games, using immense amounts of knowledge and expertise, and a lot of clever people working on all kinds of different things. And I just want to give one more example of this kind of strategy, which was the program Chinook, which was notable because for a couple of reasons. I mean, first of all, it was playing the game of checkers. And checkers is a game much like chess, and the representation was similar as well. It was, again, using this binary linear value function with all of these kind of knowledge-based features regarding kind of position and mobility and for different phases of the game, like what you do in the opening. And again, these were kind of carefully handcrafted. And it, again, did a very high-performance alpha-beta search, but also did an additional piece called retrograde analysis, which was kind of to say, at the end of the game, in certain games like chess and checkers, you can work your way backwards from all 1 positions to solve all possible endgames. And so in Chinook, they had like all of the, if you reach any position with like 10 checkers or fewer, has perfect knowledge to tell you from that position, who's going to win. It can just figure that out by searching backwards from all 1 positions into all positions with 10 checkers or fewer. And so this retrograde analysis was very important. And what was interesting about this was that, in some sense, Chinook, when we talked about the IQ test of humans against machines, checkers was interesting because, from the human point of view, it had arguably the greatest player of all time in any game, which was Marion Tinsley. So Marion Tinsley he played for his entire career the game of checkers, and I think he only ever lost 5 games of checkers in his entire career, and I think 2 of those were against Chinook. So he really was almost perfect from a human point of view at this game. And Chinook came along, and it actually technically defeated Marion Tinsley in this World Championship match in 1994. So this was before Deep Blue came along. And it was doing very well, but actually Marion Tinsley had to withdraw for health reasons, and unfortunately went on to die shortly afterwards. And so no one ever really knew if Chinook would really have gone on and beaten this greatest player. And so the guy who made this, Jonathan Schaefer, decided that the only way to really figure out if Chinook, to actually prove that Chinook would have beaten this seemingly almost godlike human player, was to actually solve the game altogether. So if you can beat God, if you can draw against God, and then you know that you've reached the highest level of play in the game of checkers. So he spent the next decades doing this, and eventually solved the game of checkers. So that means really combining this kind of Minimax search from the top with this retrograde analysis from the bottom until they meet, and actually having a perfect solution to the game. And so checkers is the largest game that was actually has actually been solved in that sense. The largest highly played game. Okay. So that's the kind of strategy that was used for many, many years. And I hope you're sitting there thinking, well, but what about principled machine learning methods? How can we bring everything we've learned to bear to do something better? And this brings us back to our self-play idea. And so, what happens if we were actually to apply our value-based reinforcement learning algorithms to games of self-play to try and find this Minimax solution? Could we actually use this? We've defined a Minimax value function. We know what that means now. We know that it is, in some sense, the optimal way to play in this game between 2 players. So can we find that value function using the same technology that we've seen so far elsewhere in the course? And the good news is that, yes, you can. And I'm not going to give the theory that proves that these things actually converge to the Minimax value function. But if you pick out like Michael Littman's thesis, for example, if you're interested, that will give you some examples where principled self-play reinforcement learning techniques do indeed find the Minimax value function or the Nash equilibrium sometimes in more general cases. So the general principle is exactly the same as we've seen elsewhere in the course. Nothing has to change at all. You don't have to do anything special to play games compared to any other domain. This is the beauty of reinforcement learning, that it applies, it's such a general idea, such a core principle, that it applies with almost no change to these different domains. And so all we're going to do is to say, well, we're going to have some value function. We're going to have our parameterization, this v of s comma w. So these are the parameters of our value function. So you can think of this as your deep network representing the value. And it's just estimating what is the minimax value from state S. And we want to adjust these parameters W so as to make them more like the true minimax value. And so we're going to use the kind of familiar techniques like Monte Carlo learning, TD lambda. And again, the idea is simply to do something like gradient descent. We're going to adjust our value function a little bit towards the return if we were doing Monte Carlo learning. So that means, if I thought I was losing, but I saw that at the end of the game I actually ended up winning, I would adjust my weights a little bit so that I ended up predicting that I was winning a little bit more. If we're doing TD, it's a bit more like, I'm playing a game, I think I'm losing the game, but then I take one step and it's like, uh-oh, I realize I've just made a blunder. Now I think I thought I was winning, now I think I'm losing. So even before the end of the game, just after that one step, we can update our value function to say, well, I thought I was losing, but I thought I was winning, but actually, after this one step, I now realize that was a bad estimate. Now I see I've made a blunder. I should adjust my estimate I had before to say, well, actually, I was really losing. I just hadn't seen that blunder yet. So you adjust your value function a little bit towards your value prediction that you made after one step. And you'll notice there's no intermediate rewards here. That's just because we're considering this common case where all intermediate rewards are 0. If you do have intermediate rewards, there would be a reward in there. If you do have discounting, there'd be a discount in there. But normally when we're thinking about games, you don't need either of those things. So these things just kind of look a bit simpler. It's just the difference between who I thought was going to win, and then after my step, who did I think was going to win. And TD lambda, same ideas, but we can use the lambda return as before. So we can actually introduce these eligibility traces and get something in between this spectrum between Monte Carlo and TD0. So one thing which is useful when we think about games, but is also useful in deterministic MDPs, so this is not specific to games, is that it's often the case that you don't actually need action value functions. So probably in the rest of this course, you've been taught that, well, to do RL, you need to have an action value function if you're doing value-based RL, because you need to have some way to estimate how good your action is in the absence of knowledge of your environment. But in deterministic MDPs and deterministic games, it's actually sufficient just to have a state value function. And the reason is that there's only one thing which can happen after you take your action. There's no stochasticity in the environment, so there's no variability in what will happen. You don't need to compute this expectation. So we can basically just say, well, in these games, this is the case where we can actually take a step forward. If you're able to take a step forward, I think a better way to say this is if you know the rules of the game or if you know the model of your MDP, you don't need an action value function because you can always just step forward once with your model or step forward once with your rules. And we call that the after state, that basically we're saying, if you want to know what's the value of taking action A from state S, you can step forward from S by taking that action and seeing which state it takes you into, and now evaluate that state that you arrive into. Okay? So I'm in some position, I play a move, I find myself in some new position, and the value of that new position is actually the value of having taken the move that took me there. Because there's nowhere else I could have gone, and I know the outcome of what this rule would do. And that really simplifies things. It just means we need to learn the state value function. If you can learn a state value function, it's a smaller object. You don't have the cross product of the state space with the action space, and things just become easier. And now when you actually just want to pick your actions, well, you consider all of these different steps that you could take, and you pick the one with the highest value. Okay? So I'm going to skip forward to do this with backgammon. So this is probably, until deep learning took off, this example here, you can think of this as something which was done by a guy called Cherry Tesaro that in a way was 15 years, maybe 20 years ahead of its time, in that it was an example essentially of deep reinforcement learning, which was very, very successful and achieved from first principles superhuman performance in the game of backgammon, completely learning for itself all strategies before anyone else had really figured out that either reinforcement learning or deep learning were a big deal and general and powerful methods for doing anything. And so I think it's really useful to look at it and try and understand what went on there, because it's really one of the outstanding examples in the field of where this really works, this idea. And so backgammon, first of all, you've got some kind of board, and the idea is that each player is trying to progress their checkers. That you roll dice, and then you move your checkers according to what's shown on the face of the dice. There's 2 dice, and you move your checkers around this way for red here, and this way for black, and eventually you've kind of got to take all of your checkers to the end of out of play, basically, and then the first player to do that wins. It's kind of like a race, except that you can land on the other player. If a player has a single checker, you can land on it and capture it, and it's sent back to the beginning again. So it's a race with those kind of interactions where you can capture each other, and you can block each other if you have more than two or more checkers on the same point. And so what happened in TD Gammon was this whole board was just kind of flattened out into a set of features to say, basically a set of features saying, do I have 1 checker in this position? Do I have 2 checkers in this position? Do I have 3 checkers in this position? Do I have no checkers in this position? And so for each of the positions on the backgammon board, there were a set of features saying how many checkers were there, a set of binary features. And so there was this binary representation that was just kind of flattened out to say what was going on in the board. And then a very simple multi-layer perceptron, which was absolutely tiny by modern standards, was put on top of that. And it output a value function estimating who was going to win this game of backgammon, given those checkers. And the learning algorithm was remarkably simple. It was really just very pure TD learning, temporal difference learning. So this neural network was initialized with random weights. It was trained by games of self-play. And it was trained using nonlinear TD learning. In other words, this TD error was computed with respect to this value function. In other words, it was exactly what we talked about. It was computing this error between whose do you think was winning in this position and whose do I think was winning once I played my move. That's this TD error. And then the weights were adjusted to correct that error. So the weights were adjusted a little bit in the direction of the gradient to make your estimate before a little bit more like what you thought the value should be having played that move. So that's basically what this rule is saying. It's just saying adjust by simple stochastic gradient descent in the direction of this error along the gradient, which would tell you how to adjust your parameters so as to achieve some particular outcome more. Okay, is that clear as an update? And so there was nothing else. I mean, it was really, that was the whole algorithm. It was really simple. There was no exploration at all. Like, can anyone think, why wouldn't you need any exploration in backgammon? How can this work? You've had a whole lecture on exploration telling you how important it is to have exploration. And yet, this works like perfectly, achieves superhuman performance without any exploration. Any thoughts as to why? Right, exactly. So there's enough stochasticity in the environment, in the dice rolls, to mean that you see the whole state space already. You don't actually need to do something special to explore to cover the whole state space. You get everywhere. And so this algorithm always converged in practice, and that wasn't true for other games. So people tried other games at this point and got very excited, and the same ideas at that time didn't work in other games. And I think partly because of the exploration issues, partly because maybe just the deep learning wasn't quite there yet. This was very small neural networks. But one of the nice things about backgammon is the dice not only mean that you don't need to explore, they also make a very smooth value function. You don't have these very precise kind of cliffs that you fall off if you just do something slightly wrong, because if you're looking a few moves ahead, there's always some randomness in what might happen, and that randomness tends to smooth out the value function and give you a nice surface to kind of learn about. So this program, having done that, it went ahead and it basically defeated the human world champion back in 1992. So that was an amazing result. It did have some search on top of this, so it was using like a three-step ahead look ahead using alpha beta search so once it had this, it was using that as the leaf value of this minimax search and bubbling those minimax values back up to the root to decide what to do. It also, back in this version which actually performed this result, I slightly lied in that one also had some expert knowledge in there. But Tesaro went back later and he showed that if you take out all of that expert knowledge, and this was just a few years later, if you take it all out and you carry on training with the version with no knowledge at all, it actually ended up outperforming the version that he'd used in that match. So this was really something which learned completely from raw data and nothing else. Yeah, question?
You said it was nonlinear, and I was just wondering where that nonlinearity was.
OK. So the question is, where's the nonlinearity? The nonlinearity is inside the multi-layer perceptron, so it takes this flattened representation of the board and it passes it through like a two-layer multi-layer perceptron, and each layer is like kind of like a linear combination of the previous one, followed by a nonlinear activation. So there was I think a tan-H activation that followed each one of those, and that nonlinearity in the middle is what makes this whole function nonlinear. And if you don't have that nonlinearity, as with all of neural networks, if you don't have nonlinearity somewhere, it just collapses to a very boring class because a linear times a linear times a linear is just a linear. And so if you want to have, it's the kind of this dilemma that, linear function approximation is so much easier and so much cleaner, and we get so much nicer convergence properties if we can work with it, but it's just not very expressive. And so if you want rich and powerful and expressive representations, you need to do something harder. You need to use nonlinear function approximation to achieve those results. And that's really why people have moved towards deep learning in the last few years. I mean, deep learning is nothing more than rich compositional functions which compose one layer, one function into another function into another function. That's what deep learning is. Yeah.
If it's a contrast where you have similar states but they have sharply differential values, does that basically force you to do more search? Is that the rule of thumb?
Yeah, I think that's probably true. So I think the sharper the value function, the more of these cliffs you have, the more precise your search needs to be, or the more accurate your value function approximation needs to be. I mean, there's always this trade-off between the quality of your function approximator and the quality of your search, and you can make up for one with the other. So, but I think, in some sense, it's expressing something fundamental about the difficulty of the problem, and you need to address that difficulty either somewhere in your toolkit. So it can be in the search, or it can be in the power of your function approximator. So it might be that you equally require more steps of look ahead internally within your function approximator. You can think of your deep network as representing kind of shortcuts to how well you can do by searching. It's kind of internally doing some steps of computation and trying to find shortcuts to figuring out the minimax value without doing any explicit search. And so that you can put more layers in there as well, and that's an alternative. Okay, so that was TD gammon. I'm going to skip this section. Okay. Should we take a little break, and then we can come back for the next part? So let's take a 10-minute break, and then we're going to talk about some more modern search techniques, which are about Monte Carlo search, simulation-based search, and moving on to what's been done recently by combining these methods with deep learning. Let's get going again. So I want to talk a little bit now about a very radically different form of game tree search, which has proven to be particularly effective in challenging games and larger branching factor games and also real-world domains. It's been very widely used now, and most recently has also turned out to be very effective even in the domains where traditional methods of minimax tree search were considered to be dominant. And so this idea is really a broad class of ideas which we can call simulation-based search. And the idea is really actually surprisingly simple. And the idea is to say that actually self-play reinforcement learning can replace search. So far we've kind of seen that there were these two different ideas. Either we could do like this minimax look ahead, where we're really kind of bubbling ahead and considering all of this tree of look ahead possibilities, where if I go here and you go here and I go there, what's the value going to be? And we can back that up and really compute the minimax values. Or we had some kind of function approximator, like a value function, that was estimating those values directly without ever doing any look ahead. And the surprising part is to say that actually the reinforcement learning can replace that first part. So actually we can use self-play reinforcement learning instead of a search procedure to actually give us a process of look ahead. And the idea is really simple. The idea is to say if I want to do look ahead from a particular state, how can I perform that look ahead? Well, what I could do is I could just consider the game that starts from that state. Consider this also applies in single agent domains where you've got some MDP, some massive MDP, and you just want to consider the sub-MDP that starts from now. And in games, we can consider the sub-game that starts from now. So you're in some root state, you're in some particular position, you're in some state right now, and you want to figure out, well, what's the best thing from here onwards? And so the idea is to simulate experience that starts from now. Right now I'm kind of talking to you guys here, delivering this lecture, and so if I'm trying to figure out the best sentence to speak next, it's more useful for me to start to imagine what those sentences might be and whether you'll be horrified at what I say or whether you'll actually, learn something from what I say, than it is to kind of imagine myself up in a mountain in the Himalayas trekking. But, if I find myself in the holidays trekking up a mountain in Himalayas, it wouldn't be very useful in that situation to then start imagining what would happen if I was standing in front of a lecture hall full of students. So it really matters to focus your learning on the subspace of experience that starts from now. You don't want to consider everything. The state spaces in general are massive. We want to consider very large, rich problems, huge domains, and we want to focus our limited resources, and our resources are always limited compared to the complexity of the real world. And we want to focus those limited resources, whatever capacity we have, on the subset of experience which we're actually about to encounter. Like there's some agent and it's about to see some set of events occur, and if it can learn to anticipate what those events are in that subspace of experience, it can do much, much better. There was a question.
So how do you deal with the opponent's strategy, or you don't necessarily know what the opponent is going to do?
Okay, so the question is, how do we deal with the opponent's strategy? And the answer is by using self-play. So what we're going to do is we're going to imagine that both I and my opponent follow the best strategy that I figured out so far. And so we're not trying to figure out what's the best response to a particular opponent's strategy. That would require some model of how that opponent behaves. Instead, we're going to again try and find the Minimax strategy, this Nash Equilibrium. And the way that we do that is by self-play, where we're going to imagine if I play according to the best strategy I have so far, and you play according to the best strategy I have so far, and then I play according to that best strategy and so forth, what would be the best behavior? And by learning from those simulated games, we can again find something which will approximate. So what we're going to do is we're going to just run experience starting from now again and again and again, and run complete games of experience that start from now, so complete sub-games that start from now, that start from this root state, and learn in exactly the same way as we were doing our self-play RL. Like imagine you're doing Tesaro's TD gammon, just like we saw in backgammon, but instead of kind of training these games from complete games that always start from the beginning, you actually say, well, right now I'm in this particular board state, and I'm just going to run thousands and thousands of games that start from this particular position and learn a specialized neural network that's dedicated to actually solving the situation from now onwards. And that would actually be a form of look-ahead search. It would learn all of the particular patterns that actually occur in the situation that starts from now, because you're focusing all of your experience on the future. And so if you have this model of the future, if you have the rules of the game, which we do in this case, we can exploit that by simulating this experience and learning from that simulated experience. So did you hear about in the previous lectures Monte Carlo tree search? Okay, so Monte Carlo tree search is a special case of this procedure. So people elsewhere tend to teach Monte Carlo tree search as like a particular form of look-ahead search with a particular structure. For you guys, I think you can understand this in a much more profound way, which is that Monte Carlo tree search is actually Monte Carlo control. It's a reinforcement learning algorithm that's applied to the sub-problem that starts from now. So instead of considering the entire MDP and applying Monte Carlo control to that entire MDP, what you can do is instead focus on the sub-MDP that starts from this particular state and apply Monte Carlo control, where you're always resetting to the beginning of that sub-MDP, and you're learning from experience of what happens when you reset only back to that particular state. You're always coming back to this particular board position, or me back in this situation here and not in the Himalayas. And you're trying to learn what happens from your simulated experience, from your imagination. Imagine again and again, what happens if I'm going to try this? What happens if I try this? And learn from your imagination what's effective and what's not effective. And if you can learn from your imagination what works well, you can actually do better. So Monte Carlo tree search is exactly Monte Carlo control with table lookup, where the table is too big to represent the entire state space. So the table is instead represented by a tree that only contains the things that you've seen so far, and you just kind of expand that tree when you get to new things you haven't seen before. And so that's what Monte Carlo tree search is. You're basically doing Monte Carlo control. You're running simulations. You're taking the average of those simulations and putting that average value back in at each step, storing that in your tree, and that gives you a way to actually search. So amongst Monte Carlo tree search algorithms, many of the most effective variants use some kind of upper confidence learning algorithm. Like when you learned about bandits and exploration strategies, you probably came across the UCB rule, which is one way to balance exploration and exploitation. And if you plug that into your Monte Carlo control, so every step you have some kind of decision about how much to explore and how much to exploit, you could also use epsilon greedy. But at every step, you've got some decision about whether to explore or exploit, and that gives you something like these UCT algorithms, which has been very, very effective in many games. And so self-play UCT actually converges on the minimax values. So this is one of those cases where although we're doing something which is basically a fundamental RL algorithm applied to our imagined experience, that might seem like a woolly concept, but actually it really converges on the minimax values. In other words, we are finding in these two-player, zero-sum, perfect information games that we're considering, this really will find the optimal solution, the Nash equilibrium, which in this case is the minimax value function. So you will be done if you do this. You'll find the right thing. And more generally, you can introduce approximations. In very large games, we'll start to introduce approximations, value function approximation and so forth. And that will give us a pretty decent approximation to this minimax value function. So it's a kind of search where we're kind of imagining what will happen. I'm imagining what will happen under my current strategy. But at the same time, I'm learning to improve that strategy from the experience I've seen so far. And that's how it can actually converge on this thing. Like I start to imagine what will happen if I try this, and then this, and then this, and you do this, and I do this. And I start to see, oh, actually, every time I tried that in my imagination, I lost. So then I'll change my strategy to do something different. And now I'll try something else where I do this, and then this, and then this, and then I win. And now I see, OK, actually, that was a better strategy. And now my opponent might need to adapt to that in my imagination and change the strategy again. And we kind of have both players continuing to improve and improve, all in imagination, starting from this state onwards, focused on this kind of subtree of possible reachable things from here onwards. So that's the idea of it. OK, so for a few years now, MCTS has been the best performing method in many challenging games. So Go, I'll talk about a little bit more. Hex, lines of action, Amazon. And I'm also going to talk about some recent results shortly where we see that actually it turns out to also perform very well in games like chess, where it wasn't, where minimax search methods like alpha beta were previously thought dominant. But what's interesting is that in many actually really interesting games, simple Monte Carlo search is enough. By simple Monte Carlo search, I mean something where we don't improve the strategy for both players, where you just kind of have some randomized rollouts to the end of the game under some simple fixed strategy, and then we just see how well that does. And that can already do very, very well in games like Scrabble and backgammon. It's enough to reach superhuman performance. Yeah, question?
In this self-play Minimax, would the two policies be the same then?
So we're basically learning a policy pair for both players. And one very sensible approximation is that the one side of the policy plays in the same way as the other side, but just with the kind of board colors reflected. But that's not a necessary requirement for this. We're basically learning the policy pair, is the way to think about it. So we're learning the policy pair, and we're improving the policy from both players' perspective, and we're playing according to that policy pair in our imagination. And each time we improve one side of that policy, we then go on and improve the other side of the policy as well. And so we're really trying to find a policy pair that approximates, that converges on the minimax strategy.
But here it's a mirror of the other one, right?
Well, it depends what you mean. Not necessarily. I mean, because different players see different situations. So it might be that one player has an advantage for playing first, for example. And so the board state can differentiate the strategy from one side to the other. So I think it's just best to think of it as a strategy pair. And it might turn out that in the way that we approximate this, that we exploit this mirroring property. But it's not like a necessary piece of understanding this. I think it's clearer to think of it as just a policy pair that is improving. And each policy, well, what's the policy doing? I mean, the other way to think of it is it's just, you can also think of this as just one policy, where the one policy sees as part of its input which color pieces it has. And so we provide this policy and it says, oh, now I'm in a situation where I've got the white pieces here and you're asking me to play a move. And now I'm in a situation where I've got the black pieces and you're asking me to make a move. But it's, in a sense, that's the policy which we're considering. That's the policy pair. We want to, so you can think of it as just part of the function approximation architecture that sometimes you're seeing black and sometimes you're seeing white. And you can do things like mirroring the colors, but that's optional in this setting. Yeah.
And can you truncate your Monte Carlo search by doing TD lambda or whatever?
OK, great question. Can we truncate the Monte Carlo search before we reach the end of the game, so we don't do full Monte Carlo rollouts, truncate and use an evaluation function? That's going to be the next part of the discussion. So let's start by doing very simple things. So simple Monte Carlo search is enough. So I think one of the reasons why simulation-based search became popular was people starting to realize that even very, very naive simulation-based searches can be remarkably powerful. So here's an example. This is the game of Scrabble. So in Scrabble, you get some letters on your rack, and you have to kind of figure out what's the best word to play on the board, and you get points according to each of your letters. And so you've got these points on your rack, you've got these 7 letters. And the idea was that the first strong program which came along in Scrabble was this amazing program called Maven. And what it did was it tried to have an evaluation function which basically said, how good is it to play a particular word onto the board? And what it would do, it would evaluate that move by the score you would get for playing that word onto the board, plus the value function of the letters that you've left on your rack. And it should probably have taken account of the board position as well, but it kind of ignored that. Okay, this was already a huge advance over humans and anything which had come before. And what it did was it just kind of looked at the rack and kind of said, well, how good is it to leave certain letters on your rack? Like if I play my blank now, which can be any letter I want, and it's really useful in Scrabble, I might get a better score, but there's an opportunity loss there because by keeping it on my rack, maybe next turn I would have got a 50-point bonus for using all my 7 letters. And so it kind of learned all of these, looked at all of these just 1, 2, and 3 letter features, like do I have a Q left on my rack? Well, that would be really bad. But if I've got a Q and a U together, that might be actually quite good because the Q is very high scoring. If I have 3 I's on my rack, that's pretty bad. There's not many choices. You've kind of lost some flexibility there. And then this whole thing was learned by a kind of Monte Carlo policy iteration. So I'm not going to talk so much about how the value function was learned because we've already dealt with that. This value function was learned by standard, essentially TD1. The value function was learned by kind of every single game, you play the game, you look at the outcome of the game, and you update the value of these function approximator to make your estimate of what happened a bit more like what actually happened in the real game. So that's the standard, what we've seen before, just like in TD gamma, but an even simpler representation. What was interesting was that the way it did search. So it actually did search by rolling out, by imagining what would happen into the future. So you'd start in this position, and it would basically just play out games according to its strategy. So it kind of play out some number of moves into the future, and then it would truncate and actually say, okay, I'm just going to look 10 moves into the future, and then evaluate the position that I think I'm in there. And it will select and play the move which has the highest average score. So if you just kind of imagine what's going to happen, just keep imagining what will happen without improving that strategy. Just keep imagining games and trying a few hundred games in your imagination and like randomizing over what you think you're going to pick out of the bag, and then just play the highest scoring move. Then this is a really, really powerful form of look ahead. And just to show how powerful it is, here's a little example of what Maven did when it actually played against the world champion. This was the first time a computer Scrabble program ever beat a human world champion, quite a while ago now, but anyway. And it beat this human world champion, Adam Logan, by 9 games to 5. And there was this one game where Adam Logan was like just way ahead in this game. And all the pundits thought this was over. There was no way that Maven could possibly come back. But Maven, with this kind of look ahead, using this kind of Monte Carlo rollouts, saw that it only had one chance to win, which was to do something called fishing, which is if you're behind, you kind of have to just hope that you can kind of find this one spectacular letter in the bag that will help you get a really high score. And the thing it fished for was it ended up picking out this word mouth part. And you'll notice that this is 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So these 2 are already down, and it had to fish to kind of hope to. It was basically predicting this endgame would work out in this one particular way, and if it picked up the particular letter, it would be able to play a mouth part. By the way, I don't even know what a mouth part is as an English word, but anyway, that's Scrabble for you. And it kind of was able to use this Monte Carlo analysis from much, much earlier in the game to realize there was only one chance for it to win and to find that chance. And of course, it was a little bit lucky as well. But anyway, it turned out to play near perfect Scrabble. I mean, there's some luck in the game, but it played very, very well. And the same ideas were very effective in backgammon. We saw earlier the example of backgammon doing kind of a little bit of search on top. But actually, backgammon, again, someone showed subsequently you could get even better results by doing this kind of very simple Monte Carlo search in backgammon. And so one way to think of these very simple search procedures is it's like doing one iteration of policy improvement. Because what are you doing? Well, you're taking your current policy, you're imagining games all the way to the end, and then you're picking a greedy step with respect to those imagined games. So the greedy strategy with respect to how well you did in those games is exactly one greedy policy improvement step. You're saying, okay, I'm going to look at how well I did in those, I'm going to evaluate it, that's your policy evaluation, to see what was the mean outcome of all of those games, and then you take a greedy step. You pick the thing the action which led to the best outcome, And so if you keep acting greedily with respect to those estimated mean values, that's doing one step of policy improvement. So Monte Carlo search is effective because it does one step of policy improvements. It's doing like one step of policy iteration. And so a natural question is, if one step of policy iteration is so powerful, what happens if we allow ourselves to do many steps of policy iteration? And so that's what leads to Monte Carlo tree search. What I want to talk about now is our recent work at DeepMind on actually taking some of these ideas further in the AlphaZero project. So it's always hard to know how much you guys know about this stuff, but I'm just going to talk about it anyway, and hopefully if you've heard about some of this before, you won't mind duplication. If you've heard nothing, I hope there's enough for you, and so forth. So what I want to talk about is how we started to bring about an architecture which, building on these ideas so far, so building on value function approximation, policy approximation, these ideas of doing some kind of simulation-based search with multiple iterations of policy improvement inside it, how we could build a system which started completely from scratch with no human knowledge at all, and was able to master some of the most complex games where previously people were using an awful lot of knowledge there. And I'm going to use Go as the case study for the beginning, and then we'll talk a little bit about other games. So why Go? Well, it's the oldest game in the world, about 3,000 years old, amongst still currently played games. There's still about 40 million active players, and there's about 10 to the 170 positions. So what does that look like? Well, there's this enormous branching factor in the game of Go, where from each of these positions, you reach several hundred other possible positions. There's several hundred moves in the game. It's a 19 by 19 board. You can place down a stone on any one of those, and that leads to a vast array of possible next positions. And from each of those situations, you've got a vast array of possible positions. And so if we were really to consider the minimax problem, doing this minimax search and really computing the minimax value, you would have to consider all 10 to the 170 of these states to actually compute the true value, like who actually has won this game, like from the beginning, what's the perfect way to play. That's intractable. And so really, the story of AlphaZero is the story of trying to deal with that intractability with principled reinforcement learning methods. And so I'm going to start by talking about AlphaGo, which was the original program that was able to defeat the world champion, Lisa Doll. And that will give us some intuitions that we can then bring into making something even more general that was able to play many games and with even less knowledge. And so the idea of AlphaZero was to use two neural networks. The first of those neural networks was a policy network. And the policy network kind of looked at the position in the game of Go. It used this convolutional neural network to kind of build up features. So each layer of that convolutional neural network is basically looking at a small region of the board, building up features which represent what's going on in that particular region of the board. And that gives you like a new layer of features saying, well, I started off knowing that these were the black and white stones here, but at the next layer, maybe I know which stones are adjacent to each other. And the next layer, maybe I know which stones are under threat. And at the next layer, maybe I've got some sophisticated idea of the kind of life and death that's going on and so forth. And so we had many, many layers of policy network. In the most recent version, this is about an 80-layer neural network. So this can get very, very deep. And what we output at the top of it are move probabilities, something to say, well, in this position, I think it's a good idea to play here. Or I think it might also be a good idea to play here, but it's a really bad idea to play over here. And we represent that as kind of like a probability map, like a probability distribution over the legal actions in the game. OK? And there's a second neural network in AlphaGo, which is called the value network. And the value network is also a convolutional neural network, which takes the board as an input. It looks at all of the black and white stones, builds up features of features of features to get more and more sophisticated representation of what's happening in that position. And at the end of it, it outputs a single scalar number saying who it predicts is going to win the game. Like +1 if you think white is going to win, and -1 if black's going to win. OK. So that's the value network. And so this is a form of value function approximation, and this is a form of policy approximation. And the idea is that in the original AlphaGo, we trained these two things by, first of all, supervised learning. So we started with human expert positions. And I hope you're thinking, oh, I thought we were doing reinforcement learning here, so why do we need to take human data into account? And we're going to address that later. Okay, so we started with human expert positions. we trained our policy network to mimic what human experts did in each of those positions. So in each board position, we said, OK, in this position, the human played there. And so we adjusted the parameters of our policy network to say we want the policy to output that same move that the human played. We just adjust the parameters of our neural network to predict the move that the human played. So that's straight classification. Once we've got that policy network, we apply reinforcement learning to that policy network. In other words, we actually got this policy network to play games of self-play against itself, and we adjusted the policy network further by reinforcement learning, by a policy gradient method, but also we built up this value network. What we did was we built a value network which, from each of these games, it was kind of like a Monte Carlo learning of the value function. That we played the policy network against itself, and we looked at the outcome. And then from each of the positions that we encountered in that game, we asked the neural network, the value network, to predict who was going to win. So if you pass in this position, the question we're asking is, do I think black is going to win from this position, or do I think white's going to win from this position? And the way that we actually build the data is by getting the policy network to play against itself. And so if at the end of the game, the policy network, which was very strong, ends up with black winning, that's the target that we provide to our value network, and we adjust the parameters of the neural network to make it provide an output answer saying it thinks that that player is going to win more. OK? Any questions?
So would we update, like if black wins, would we update, oh, +1 black wins for each of the state projection, for each of the states that we think of?
Yeah, so for every state that was visited during this, so so think of this process as classification, and this process as regression. At this step, what we're kind of doing is building a big data set that contains all of the positions that were encountered during all of these games of self-play. And from each of those positions, we're trying to predict who ended up winning that game of self-play. That's the regression problem we're trying to solve. Like from every position, who ended up winning. And if you can predict that, if you can predict who ended up winning in this game, that's a really powerful thing to have in your arsenal. Like this is why value networks are so powerful. They summarize, they're kind of a cache of all of the look-ahead that you might do. This is also true in single-agent domains. It's why we build value functions, that you want to have a summary that tells you one shot immediately what's the value of being in this situation without having to do all the look-ahead and consider all of the possible things which might happen in the future. So it's like a summary of all of the future possibilities without having to do this exponential expansion, combinatorial expansion of all of those possibilities.
If you have bad examples in the supervised learning stage, to what extent can it unknow what it's been given?
Yeah, so the supervised learning can have bad examples in there. The self-play reinforcement learning can correct those by adjusting the policy network, and that stage was important in practice. But we'll see a better way to do that where we don't even start from human expert positions shortly. And in fact, our best results come from not using human data at all subsequently. OK. So again, if we think of this enormous search tree which we're trying to compute, so this could be Go, but it could be any other game, but Go just has a particularly daunting search space. And here we're just showing like a binary search tree. It's kind of like a cartoon of what happens in this search tree. And we can see that from this little situation, we could go over here, we could go over here, and then there's all of these possibilities. And the real search tree is like this, but there's kind of 200 possibilities from each of these instead of 2. And it's kind of the depth is about 200 as well. So it's a big search tree. And how can we narrow that down? Well, the first idea is that we can reduce the breadth of this search tree by using the policy network. In other words, we don't have to consider the full breadth of all possibilities. Like there might be this enormous branching factor of 200, but if our policy network tells us that the sensible move to play is this one, the policy network can basically pick out a handful of reasonable possibilities and can be relied on as kind of soft pruning mechanism where we can exclude the moves which the policy network says are nonsense and only come back to those later in search. So we kind of prioritize the things that the policy network thinks are good, and that immediately gives us a much narrower search tree. And that's why the policy network is effective in this search. And the second thing we can do is to reduce the depth by using the value network. And this is just like we saw with Deep Blue and all those programs in the past, where what we can do is instead of going all the way to the end of the game, we can summarize the subtree beneath each of these leaf nodes by a single value that estimates who's going to win from that point onward. Again, a value function is powerful because it's like summarizing in one number all of the possible contingencies from that point onwards. And if you have that one number, you've saved yourself all the effort of having to do that future computation. This is why value functions are so crucial. And so we can use this value network to save us from having to build out and search for this big subtree over here. And that makes a dramatic difference to the size of this search tree. So putting those together, we built a Monte Carlo tree search algorithm in AlphaGo. And I'll just step through that in a little bit more detail for those who really want to see, what would a state-of-the-art like Monte Carlo tree search actually look like? How does it kind of put these pieces together to give you those properties? And it really kind of has these three strategies. This is the strategies that we use in our latest version of AlphaGo. And the first phase is you've got to kind of select a path. So remember, we're always doing this thing where we're simulating a game. We're kind of imagining what's going to happen next. So we've got this choice of, well, what should we imagine? What should we imagine? Like, what should each player do in each of these imagined situations? And the way that we pick the actions in our imagination is by maximizing these Q values, like these action values, which we'll explain where they come from in a minute. But for now, just imagine that for each action, we're storing some kind of Q value saying how good is that action. And so the greedy strategy would be just to maximize Q. But the problem with the greedy strategy is it can get stuck. You need some kind of exploration in the search tree. You need to sometimes try some other branch, not your greedy one, just to see in case that other branch actually turns out to be better. You have to try it sometimes. And so what we do is we do something like we saw in the exploration lecture, where you want to add in some upper confidence bound, U here, and that encourages it to consider things which might be good. So if your upper confidence bound U, this upper confidence bound term U here says that you might actually be able to get a lot more value than Q, then we'll take this path here, even if this one currently has the best Q. Okay, so we just add on our Q value with some upper confidence term, and we maximize that, and that picks out a path through this search tree. And the upper confidence term is actually really simple. It's just proportional to, so it's proportional to the policy network. So basically, if the policy likes something, it will take it more often. So that's implementing this idea that the moves that the policy network likes are tried, and the moves which it doesn't like are excluded. So this U is just proportional to the policy network, to the policy probability, and it's inversely proportional to the visit count. So the more you try something, the less of a bonus you give it, because you've already kind of got some idea of what it is. And that turns out to have some justification. I won't go into that. So we've selected some path now through the search tree. So we're just kind of imagining things again and again and again. So each simulation, we're going to start from our root state. We're going to imagine what happens according to this strategy of trying some imagined path through this imagined game, through the imagined world. And then we're going to once we reach the end of we reach some leaf node here, what we're going to do is evaluate that leaf node and expand it. So we evaluate it using our policy network and our value network to give us move probabilities from our policy network and a value from our value network. And you only need to do that once per simulation. And once you've got that, you back up those values. And so here what we're saying is that this is the Monte Carlo part, that the Q value of every action in this tree is just the mean value of all of these V's that we've computed in the subtree beneath it. It's just a mean. It's just a mean of all of the simulations we've tried. So what we're trying to say is that, how good is this action here? Well, this action is the mean of the outcomes of all of the simulations that I tried that started from this action here. That's the Monte Carlo idea, right? That you try something, sometimes you win, sometimes you lose, and you just take the average of it. So if you played 3 games and you won 2 and you lost 1, well, your action value would be 2/3 here. So you're just taking the mean of everything that happens beneath you. So this one here, this pink Q, is taking the mean of the leaf values that you saw beneath that. This green Q is coming from here, and so forth. And once you've got those Q values, you cycle back round, and you use that to influence your next trajectory. So this has got that policy improvement happening, where not only are we using our current knowledge to influence the path we take, but we're actually improving that knowledge in this stage here. We're improving our knowledge in the search tree And that improved knowledge, now we figured out, oh, actually, turns out now I see that this was actually a bad idea. And that influences the next trajectories that we take. And those next trajectories will become better and so forth until eventually this converges on the Minimax strategy. OK, so that's the Monte Carlo tree search strategy. So we went out and we played against Lisa Doll, who was the winner of 18 world titles. This was in Seoul in March 2016. And AlphaGo actually won this match 4-1 and became the first program to beat a human professional player. And yeah, I've just got, for those of you who haven't seen this, I've got a little video here. This was the first time a computer program had defeated a human pro player. This was actually the machine that played the match. This was sitting in a data center within Google in the US somewhere. You can see the little board there. But actually, we were in Seoul operating over a connection to that data center. And this led us on a path to try and do something which was simpler and using less knowledge to try and achieve even more performance. And just to finish, this is some of the events that happened there. Yeah, this is the actual match taking place with Aja Huang, who is one of the developers of AlphaGo, playing against Lisa Doll there. This was the press room, which was a little bit crazy. This was actually what we were looking at in the room watching the match there. Actually, this is the program, our statistics. We're not influencing it, but just kind of watching it on these screens and making sure that nothing is falling apart and the connections are up and so forth. And that was us receiving a 9-down certificate from the Korean Go Association. So this led us to a quest to try and do something without human knowledge. Like, the goal here should be to have a system which can crack any domain. I mean, we're talking about games. Of course, we would like to go beyond games, but within games, within this class we've been looking at, what would be the system which would be most satisfying? Well, it had a few properties. It would start with no human knowledge at all. We would just provide it with the rules of the game, and it would go out and it would learn how to play that game to a superhuman level of performance. And so we tried to set out to do that within this class of two-player, zero-sum, perfect information games. And this led to the AlphaZero project. And so we wanted to throw out anything to do with humans. So we threw out human data. We wanted something which learned solely by self-play reinforcement learning, starting from random, with no human features, so only taking the raw board as an input, so no handcrafted features or anything like that. We used just a single neural network, actually, in AlphaZero. So the value and policy networks were combined into one neural network, which actually led to a big improvement for interesting reasons. And it had a simpler search algorithm. So it was really a very pure search algorithm. And the idea here was to say, each time you take complexity out of your algorithm, you achieve more generality. Or the converse is true as well, that each time you specialize your algorithm to something in your particular domain, you kind of handicap yourself at the same time because you're introducing something which has blocked you from that same idea working somewhere else. And so the idea should be that we have something very pure which can generalize to other domains with minimal effort. And ideally something which is, nothing, where there's nothing really special case to games at all. So this led to the AlphaZero algorithm. And the idea is really simple. And the idea is actually to do something akin to policy iteration. And so I'm just going to talk through this strategy. And hopefully you'll get the algorithm as a fairly straightforward idea, which is that, in each of these positions, imagine this is your Go game, we're actually going to play games where from each of those positions we're going to run a search, we're going to run one of our Monte Carlo tree searches using our neural network. So inside this, we've got our MCTS, as we saw earlier, guided by our policy and value network. And we run that search and pick a move. Okay? And given that move, we play it. That takes us to a new position. We run a new search using our neural networks, play that move. Run a new search, play that move, until we get to the end of the game. Okay? And that's how we generate our games. So the AlphaGo is pure self-play. It's playing against itself, starting completely randomly. So we can initialize these neural networks to completely random weights and start off by playing random games, but influenced by whatever those neural networks happen to think is a good idea. And then what we're going to do is use those games that we've generated to train our neural networks to do better. So first of all, we're going to train our policy network to predict the move that was played by the search. Like, what did AlphaGo actually do in that search? Well, it was in this position. We ran our policy network, and that policy network actually picked some move. Well, now we want to train our policy network to do the thing which the whole search did before. So we're kind of distilling the whole of that Monte Carlo tree search back into our policy. So we used our policy to influence our search. We ran this huge search, like looking ahead tens of moves and running like 1 million simulations, and now you want to kind of distill that thing back into a simple decision that's made by your neural network. In other words, the way to think of this is we want to train our policy network on the best possible data that we could have. And where does that best possible data come from? Well, it doesn't come from humans. It actually comes from AlphaGo itself, that we should trust those moves which it produces as the best possible targets for training a new generation of AlphaGo. So we train the policy network to predict AlphaGo's moves. So we take whatever that search did, that becomes the target for classification for our policy network to predict those moves, not the human moves. And we also, at the same time, train a new value network by regression to predict the winner. So whatever the winner of that self-play game was, from each of these positions that we encountered, we now want our value network to be moved to predict that winner. So we were in this game, we ended up with some actual outcome with some winner, and now that winner is fed into all of the positions that led up to that win. So we're basically saying from each of these positions, predict who actually ended up winning when AlphaGo played against itself using search. And so we've put the search inside the loop of reinforcement learning. It's a kind of search-based policy iteration, where each generation we're making a new policy and a new value function and a new policy and a new value function that builds on the last one with search in the loop. And the idea is that when you learned about policy iteration before, let me have a slide on this. Yeah. When we learned about policy iteration before, we saw that policy iteration uses this idea of greedy policy improvement typically. You take your policy, you evaluate it to give you a value function, and then you act greedily with respect to that value function to give you a new policy. But in AlphaZero, we do something much more powerful, which instead of acting greedily, we perform a huge search to kind of figure out the best strategy. And search gives a much bigger policy improvement than just acting greedily with respect to your value function. You can do like a multi-step look ahead to give you a much better policy improvement than just this one-step jump that you get from policy improvement. In other words, you run a big search, and that big search leads to an action selection procedure which is much better than the thing that you started with, than your raw policy that you began with. Like the search itself you can think of as a policy, a way to pick actions. You run your search and you do the thing that was recommended at the root. That is a kind of policy. And that kind of policy is massively more powerful than the policy you start with. And so that kind of iteration actually helps you do better and better and better. And so what we do is we feed this back in again and again and again. Iteration by iteration, the new policy and value network is used in the next iteration of AlphaGo 0. And that goes round and round and round, leading to better and better results. And we start off with completely random weights, but very quickly this thing learns how to get much better policies. And each generation, we get this massive improvement due to the search, which leads to the next set of data being produced being much higher quality than the previous. And this happens completely online, so we're always training on the freshest data produced by the freshest policy and value network, and it goes on and on and on. So we could think of this as building on other work which has come before, like Lagoudakis, Scherer, and so forth, where people have looked at other ways to do this kind of policy iteration schemes. But here we're really putting the whole of search inside the loop, and that leads to a very, very big improvement. So the policy improvement makes use of the search to improve the policy, and the policy evaluation makes use of search as well, that each time we run a game, we're running a game where each player is picking its move using search. And so the self-play is like self-play with search in the loop. Like AlphaGo plays it runs a search, it plays a move using search, plays another move using search, plays another move using search, and eventually the outcome you get of that game is like gold. You know, that outcome you get is really, really high quality. And so when you train, that kind of policy evaluation is much more useful than if you were to get your raw neural network to play against itself and then look at the evaluation of that game. Like the search gives us very high quality outcomes. And so that's why AlphaGo 0 is so much more effective than the previous version of AlphaGo. So this leads to much more sophisticated play over time. As you start to train this thing, you start off with, you start to see it starting off with completely random weights. After just a few hours, it starts to behave in the way that human beginners do, starting to like chase after stones and try and capture them greedily, a bit like human beginners do. But after just a few more hours, it starts to play like a strong human player and understand all of the concepts of Go. And after around 72 hours, it was superhuman. So this is an example of a learning curve. So you get this very nice stable learning. And this is typical of every time we've tried this in every game, we see these very stable learning curves. This is actually repeatable. If you try again, you get similarly stable learning. And this shows it. This is the version learning completely from scratch. And this is the version that beat Lisa Doll. So this is a much, much stronger program there. And it exceeded that version after about 72 hours. Oh, there we go. OK. So one way to evaluate AlphaGo is how well does it compare to humans and the previous state of the art. So the previous state of the art before these algorithms came along were programs like Zen and Crazystone, which are very sophisticated Monte Carlo tree search programs using a lot of the ideas that we've talked about, but building on massive amounts of human knowledge as well to try and bootstrap their performance, rather than relying entirely on principled self-play reinforcement learning with deep neural networks. And so the original AlphaGo, when it came along, this was in our Nature paper, beat the European champion Fan Hui by 5-0, and that represented like a 4-stone. These gaps here show what happens if we got this version to play this version, and this is like giving 4 free moves to the opponent, and it was able to beat it. We were then able to, the version which played against Lisa Doll was able to give 3 stones advantage, like 3 free moves to this version, and still beat it. These are slightly, you should take these with a slight pinch of salt because these are programs which are trained by self-play, and so they're particularly good at beating weaker versions of themselves. And so it's not clear that that would generalize to a 3-stone improvement against humans. In fact, it almost certainly wouldn't. And then the version which we played online and beat the top human players 60-0 in the world, and that version was called AlphaGo Master, and that beat the AlphaGo Lee by 3 stones, 3 free moves against that version. And then most recently, this is the version AlphaGo 0, which I've just been talking about, which was completely learned from first principles. And it was able to beat that version about 90% of the time. So if there's one thing to take away from this, it's that really doing things in the principled way, you have to believe in your principles, and you have to believe that you can overcome all of this knowledge that it feels like you should be building into the system. But actually, each time you put knowledge into a system, you're really handicapping it. And if you really go back to the beginning and find the right principle to learn for itself, it will do better eventually. And we saw the same in backgammon, but the same is true even for the hardest problems within this sphere, like Go. OK. So it learns human Go knowledge, and this is just an example where it discovers like these human patterns that humans play in. So humans in the game of Go have spent about 3,000 years developing this theory of how to play. There's actually, you can take degrees in the game of Go, and there's universities devoted to studying it. And there's a whole theory of how to play in the corners, which was discovered by AlphaGo during AlphaGo Zero during its opening play, but ultimately discarded later in favor of new openings that humans didn't know about. And there's actually a lot of creative moves that it's discovered and played over time. And so, of course, our goal is, it's all very well to say, well, this is a more general algorithm, but nothing is really general unless you prove it's general by trying it in more than one domain. And so we tried AlphaZero in 3 games, chess, shogi, which is the game of Japanese chess, and the game of Go. So so chess is interesting because it has this whole history, as we saw with Deep Blue, where massive amounts of handcrafting have gone into building like these really super-powered computers with decades of experience, where chess was the Drosophila of AI for decades, and the level of performance that's been achieved in chess is immensely superhuman. Shogi is interesting because it's actually only just reached the point where computers are able to play at the level of the top humans. And it's quite different to chess, actually, because when you capture a piece, you get to put it back down again as one of your own pieces. So that's like a really dramatic difference to the game and the game of Go. So chess has a smaller branching factor than Go, but it's nevertheless interesting for other reasons, because it is arguably the most studied domain in the history of AI, and that we have these highly specialized systems, such as Deep Blue, and the state-of-the-art programs now are programs like Stockfish, which are indisputably superhuman. Shogi is computationally harder than chess, and all of these state-of-the-art engines are based on alpha-beta search. And they use huge amounts of knowledge to go into them. There's all of these heuristics and extra pieces that go into making them really, really strong. And each one of these little kind of phrases here is some, big advance that was made by kind of putting a big piece of knowledge into the program, or a big advance to these programs. And so there's these really beautiful pieces of programming like Stockfish, which use all of these things. And AlphaZero just throws that all away and says, let's use self-play reinforcement learning with self-play Monte Carlo search, these methods that we've seen so far. And in each of these games, within just a few hours, actually, it was able to outperform the world champion. So in 4 hours, AlphaZero surpassed Stockfish, which was the state-of-the-art program in chess. In 2 hours, AlphaZero surpassed Elmo, which was the world champion in the game of Shogi. In 8 hours, AlphaZero surpassed the version that defeated Lee Sedol that we looked at earlier. It won against the world champion Stockfish, 28 wins and 0 losses. And this is just showing that in each of these games, it produced very, very strong performance. And this is actually a figure from the Financial Times year-end charts that came out in December. This is brand new, by the way. All of this work came out in December. That just kind of showed, I thought this was quite nice, it showed how computer chess has progressed over the decades. So this is actually the state-of-the-art in computer chess on an ELO scale that kind of shows how much they've progressed over time. And you see, this is the top humans in the world, and you see at this point here was Deep Blue. It was like a spike where they built this special hardware and really performed very well. But actually, they continue to advance right up until now. They've just advanced and advanced and advanced, and then you carry that forward, and this was AlphaZero kind of doing the same, but in 4 hours. So, and it scales very well with search time. So actually, this Monte Carlo tree search actually scaled better than alpha-beta search, which was thought to be something with the only method that would work in the game of chess. So I just want to finish with saying, this is just one example of how to use all of these methods. And so far, we've talked about these games as like classic board games as a case study for AI. But of course, they're just a stepping stone towards where we really want to get to, which is actually systems that learn completely from scratch using very principled methods, starting just from the raw inputs and without human data to learn to achieve human levels of performance in very rich domains that we might care about. And actually simulated games, such as this one, are sometimes a more useful test bed for us. And this is an example of an algorithm. It's actually the Unreal algorithm, which was learning just directly from pixels to try and solve these kind of domains with 3D navigation, just looking at the pixels and learning how to achieve the reward of picking up the apple and solving quite interesting and challenging problems. And a lot of the same ideas which we've talked about are relevant. And I think, hopefully, if there's something to take out of this case study, is that these ideas of learning from scratch are principled, they work well, they achieve optimal performance, they can reach superhuman levels, and the same ideas are applicable not just in games, but everywhere else. We shouldn't have to special case in any way to games. So I'll leave that with you. Thanks very much. Hope you enjoyed the course. And yeah, I'll be here for a couple of minutes if people have questions.